So the first issue is there's an exam scheduled for today, but I let time get away from me and didn't notice. So I always plan on giving you about a week heads up before an exam. So we're going to push this one back. So exam 1 is next Tuesday, which is the 4th, I think. And for topics, let's just make the conservative call, and it's everything up through particle statics. So there'll be a lot of free body diagrams, there'll be vector stuff, and then there'll be particle statics. And if anybody, if that makes it hard for anybody moving the exam from what's on the syllabus, come talk to me and we can work something out. Anybody have any questions about the exam? Oh, one thing. So I think I mentioned this before, but you know, for the quiz was all short answer stuff, and to get ready for that, you read your notes. To get ready for the tests, the exams, you just want to go over problems and understand the thought process in the problems as well as you can. There are 2 homework problems I want to do to start with. I want to do number 2 on particle statics, and then I want to do 5. Really, it's only the 3rd part of number 5 that I want to do. Well, probably not. We'll see where we get, but any new stuff today I think is not going to be on it. Okay, so particle statics, number 2. Okay, so this one, there's an incline that makes an angle at 30 degrees with the horizontal. Yeah, so now you get to relive all the fun. I think this is the one where okay, yeah. Oh, that's a horrible rectangle. Okay, so this one is 50 kilograms. This one is 20 kilograms. There's an unknown force that's parallel to the incline. So that's F. And then there's a 100 Newton force coming down. Bless you. And it breaks it up into parts, but really you have to solve for everything together. So we want to calculate the normal forces that the ground applies to each of those 2 things. We want to calculate the reaction forces that the carts apply to each other. And we want to calculate F. So we're assuming that this is in equilibrium. So if it's in equilibrium, what do we know about the motion of those 2 carts? Yeah. Oh, in the ones that show wheels, those are ways of saying that it's frictionless. toward the end of the class, we'll talk about friction in wheels. But for now, we're always assuming that wheels are frictionless. And then if it's just a box that looks like it's sliding, it'll either say that it's frictionless or that there's friction. Should. Okay, so what do we know about the motion of these two things if it's in equilibrium? Acceleration is 0. So there's two possibilities. It could be moving with a constant velocity in any direction, or it could be at rest. Either way, the answers are all going to be the same. Okay? All right, so to calculate this, we know we're going to choose a body to isolate. We really have three good options. I mean, you have infinitely many options because you could break things up into pieces of a wheel and whatever, but there are three plausible options here. You can isolate the system of both carts, and or you can isolate the cart on the left, and or you can isolate the cart on the right. And it turns out that you can do this problem with any two of those three possibilities, okay? But you're going to have to do two free body diagrams and two sets of Newton's second law, 2 times using Newton's second law. Well, what I'm going to do is just isolate the two individual carts. So let me start with the 50 kilogram. There's a weight force acting down. That's 50 times 9.81, so 490.5. And then down at the ground, there's the normal force. I'll call that N50. And then keep going around counterclockwise. There's a pushing force from the 20 kilogram cart. I'll call that R. There's nothing at the top. And then there's an F that way. And there are two choices here. We could use a rotated coordinate system like you always did in Physics 1 on problems like this. And then we have to figure out the angle, come up with the components for the weight force, but everything else is easy. That's probably the easiest way to do this. Or you could just use the regular coordinate system and come up with the angle theta that represents each one of those forces. I think that's what I'm going to do. So before we go to Newton's second law, let's figure out what these angles are. So what angles do we know? Well, we know that the angle between the horizontal and F is 30. That's exactly what's given. So I'm going to start with that. Okay, so that's this force F. And for that one, to go counterclockwise from the x-axis is 30 degrees. So theta here is 30. Weight force we don't have to worry about. This force N50 is 90 degrees counterclockwise from F. Okay, so that's this force N50. And the angle for that one is go to 30 degrees to point in the direction of F, and then go counterclockwise another 90 to point in the direction of N50. So this is 120. And then we need the R vector. That's exactly opposite that force F. So you can think of that as 30 plus 180 or another 90 plus 120. So theta for this one is 30 plus 180 Yep. Let me just write out the, so this one, I got this by saying this is 30 plus 90. And then we can go to Newton's second law. So we have the weight force, 0, negative 490.5. And then we have F times cosine and sine of 30. And then we have N50 times cosine and sine of 120. And then the last one is R times cosine and sine of 210. So that gives two equations. The first one says 0.866F plus 0.5 N50 minus 0.866R is equal to 0. And the second one says, so I'm going to, instead of having negative 490.5 on this side, I'm going to make it positive 490.5 on the other side, just to set it up for the equation. So we have 0.5 F plus 0.866 N50 plus, that's going to be a minus 0.5 R is equal to positive 490.5. Which one is it supposed to be what? All right. Okay, so can we solve that? Well, we have 1, 2, 3 variables and 2 equations. So 3 equations, 2 variables. No, the opposite of that. 2 equations, 3 variables. And so we know that we have to isolate another body, at least one more. You know, we have to, the number of equations have to catch up with the number of variables. So I'm going to isolate the second one, the 20 kilogram. Okay, well, we have a weight force that's 20 times 9.81, so 196.2. And we have a normal force, N20. And there's nothing acting on the right side. There's 100 newtons pushing down perpendicular to the top. And then the only other thing is the contact force that's applied to the 20 by the 50. So that's this way, and that has a magnitude of R. Okay, and that's it for the second one. And we already have vectors with all these directions, I think. Well, maybe not the 100, actually. We don't have one that's, so let me do that one. I think in some ways, like how well you do in this class has more to do, like there's not a lot of like big ideas in this class. So sometimes like the biggest ideas aren't really the things that that determine how well you do on tests and in the class overall. I think in a lot of ways it's the little things more, like can you figure out those angles for different vectors, you know? Can you represent the unit vectors the right way? So anyways, I'm gonna do this for the 100. So let's see what we have. Well, we know that we've already figured out that the normal force is in the direction theta equals 120. That 100 Newton force is exactly opposite that. So we know that this angle is 180. This is the 100. And so 120 plus 180 is 300. So Newton's second law says we have 0.866 R, 0.5 R. Plus the weight force, 0, negative 196.2, plus the normal force, so that's negative 0.5 N20, positive 0.866 N20. And the only thing we have left is the 100, so that's 0.5 times 100 is 50, and then 0.866 negative times 100 is negative 86.6. And 1, 2, 3, 4. So that's all taken into account and added up, and it's equal to 0. So our third equation says 0.866 R minus 0.5 N20 is equal to negative 50. And the fourth equation says positive 0.5 R plus 0.866 N20 is equal to, can I do that in my head? 182.8. So now we have 4 equations. Did we add any new variables? Yes, we added N20. That wasn't there before. So now we have 4 equations for 4 variables, and the variables are was going to get really mad about that, but then I remembered that it hurt my voice when I did that last time. So the four variables are, what do we have? F, R, N50, and N20. So we should be able to solve it as long as, I mean, it's possible that one or more of those equations is a linear combination of other equations. And then when you plugged it into your calculator, it would say no solution. I think it's safe to say always for the problems in this class, if you do that and your calculator says no solution, you just made, there's just a mistake somewhere. I mean, all of these are solvable. So 4 equations, that means we're going to have 4 rows and 5 columns. So these are equations 1, 2, 3, and 4. And the variables I'm going to do in the order there. So F, R, N50, N20, and the constant. Okay, so for equation 1, F's, we have 0.866. R's, we have negative 0.866. N50s, we have negative 0.5. Okay. And then go to equation 2. F, we have 0.5. N50, we have 0.866. R, we have negative 0.5. 0, N20. And this time the constant is 490.5. And then the third equation, R is 0.866. N20 is negative 0.5. The constant is negative 50. These are zeros. And then the last one, R is positive 0.5. N20 is positive 0.866. The constant is 282.8. And then these two are zeros. And if you do reduced row echelon form, you get the same size matrix back. What am I doing? I didn't make that so little. Okay, so there's 3 here, 1 here. And you'll get the 1s down the main diagonal, zeros everywhere else, and then your answers are just in that last column. Nobody happens to have these answers, do you? Oh. Okay, sorry, what was For R is what? Okay. 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 So this one is F, R, N50 and N20. And it's worth noticing in problems like this because a lot of times, I mean, there's so many numbers that you're entering, it's easy to get a number wrong. And so anytime you can look at it and check for certain stuff that's going to give you more or less confidence in your answer, you know, if you can find something that would tell you that something went wrong, it's really helpful. Well, look for the forces that you know are in the right direction, okay? So we know that this is a pushing contact, okay? So that R has to be that direction. And so, in other words, if we got a negative answer for that variable R, something went wrong. Same with the normal forces, right? A negative answer for R, either the normal forces would say that the other card is pulling on this one, or the ground is pulling down on it, and that can't happen. So anytime you know the direction of the force, those variables have to come out positive. Okay. Same thing is always true with cable tensions. All right, any questions about that? So, you know, I think a couple people have asked me, like, how do you know what to isolate? Like, how do I know to isolate? How do I know to isolate the two cards? Or how do I know this one I isolate the whole system together and then one of the cards for that? Really, the answer is just isolate something. Do Newton's second law. Count up the variables. Count up the equations. And if there's more variables than equations, isolate something else. And keep going until you catch up. You know, there's not really any science to it. Eventually, I mean, once you've isolated all the bodies, if you still have more variables than equations, there's nothing you can do with the statics. And there are problems like that. They're called statically indeterminate. And in problems like that, it turns out that you can come up with extra equations by knowing something about how the body deforms. And that's something that you learn about in deform in engineering. What do you call it? Mechanics of materials, or deformable body mechanics, we call it here. But in this class, if you have too many variables, you just have to isolate something else and just keep going until you catch up. Okay. All right, the other one I wanted to do is number 5. So this one, the angle is 20 degrees. The mass is 20 kilograms. And there's a force, a horizontal force of 50 newtons. And we want to calculate the force vector applied to the block by the incline. So the force on the block by the incline, FBI. And we're just using a regular coordinate system for A and B. So notice, like, when you did a problem like this in physics 1, you would choose a coordinate system where the y-axis was pointing out of the incline, okay? There are a lot of problems in statics that's not necessary. And the reason is we're not using coefficients of friction and stuff, so there's no reason that you have to break it up into a normal force and a friction force. It's just a vector, just an unknown vector. And the second one, what's the force vector the block applies to the incline? So that's the force on the incline by the block. And then the last one, this is the one I want to talk about. Calculate the normal force and the friction force. And I want to talk about this even though you don't have to worry about, like, I'm not going to put this on the test. But I do want you to see something new here that's going to come up later on and be helpful. And in D form, it's going to be super important. So there's nothing like part C on the exam that you have to worry about. All right, so first I'm going to do a free body diagram. There's a weight force of 20 kilograms times 9.81, so 196.2. And then there's a friction contact between the block and the ground. So we're just going to represent that as unknown components in the X and Y direction. So this is our force F on the block by the incline. And then there's the horizontal force of 50. And so Newton's second law says 0, negative 196.2, plus negative 50, 0, plus FBIX, FBIY, is equal to zeros. And so the X component of FBI is 50, the Y component is 196.2. So the force on the block by the incline is 50, 196.2. Any questions about that? Okay, so, and then part B is just Newton's third law. We know that the force on the incline by the block is negative force on the block by the incline. And so that's just negative 50, negative 196.2. Okay. And now for part C. So this stuff isn't on the test. But we want to take the force on the block by the incline and figure out how much of that force vector. So that force vector, I mean, let's draw it. Okay, so we have, so here's the block. Let me draw it a little more. That angle's only 20 degrees, so let me try to draw it a little more accurately. All right, so we have this 50 Newton force here. And we have the weight force, 196.2. And then we calculated that the force on the block by the incline is 50, 196.2. So it's about 4 times as tall as it is to the right. So something like well, that's like, I don't want it to look, let's say it's like this. Okay. That's the force on the block by the incline. Well, we know what the components are, but that force vector is made up of a normal force and a friction force. That's what it is. Even though we didn't break it up that way to calculate it. Okay, so now what we want to do is break it up into a force that's parallel to the surface plus a force that's perpendicular to the surface. Okay, and this would be the friction force, the one that's parallel to the surface, and this would be the normal. Okay. And one way to do that, any questions about that? One way to do that is if we could express this force vector FBI in a coordinate system that's oriented like this, okay, then the normal force would be the Y component and the friction force would be the X component. That's what you did in physics 1, okay? You just started with this coordinate system. So we already have this force vector expressed in one coordinate system and we want to re-express it in another one. And the way to do that is, the easiest way to do it is with a rotation matrix. You know, if you have a calculator with you that does matrix multiplication. So if you have a vector in coordinate system A, and you want to express it in coordinate system, you want it in coordinate system B, then find the counterclockwise angle theta that takes coordinate system A into coordinate system B. Then your vector, I'll call it U, in coordinate system B is cosine theta, sine theta, negative sine theta, cosine theta, times your original vector. This looks complicated, but when you get used to it, it's quick. So back to the problem. Our coordinate system A is like this. And we want to go to coordinate system B like this. What's the counterclockwise angle that we need to start at A and end up at B? That's right. So theta is equal to minus 20 degrees. And so this matrix is cosine of minus 20, sine of minus 20, negative sine of minus 20, cosine of minus 20. And that's 0.940, negative 0.342, positive 0.342, 0.940. And so the force on the block by the incline, expressed in this new coordinate system, so I'll write that as like new, is equal to 0.940, negative 0.342, positive 0.342, 0.940, times our answer from the original coordinate system, which was 50,196.2, could someone multiply those for me? Someone who's done matrix multiplication on their calculator before. Okay, negative 20.1, did you say? Okay. Oh. So that says that, well, it says that I drew that friction force backwards because it turns out it's actually going in the negative UX direction. But the Y component of that vector we got is that normal force, and the X component is that friction force. So this is the force of friction, and this is the normal force. So any vector that you have expressed in one coordinate system, you can express it in a rotated coordinate system with just this matrix multiplication. And I mean, I don't expect anyone to feel like comfortable with that yet, but that's something that's useful, and we'll talk about it more here and there as this class goes on. Okay. So now we're going on to the next topic. And that is rigid body statics. So with particles, we assumed that, you know, we treated the bodies like they had no length dimensions. And we got rid of any orientation information. Now we're going to include both of those. So with rigid bodies, we'll have both of those. And because now forces can happen at different points, can be applied at different points. We have to introduce the idea of a moment. People just call it a moment, but what it really is a moment of a force about a point. A moment, by the way, is just a mathematical term. That's why you see that come up in a lot of things. Area moment of inertia in D form, mass moment of inertia in dynamics, moment of a force. They all just meet this mathematical definition of a moment. That's why they give them all sort of these matching names. So, okay, here's the moment. And I think it's a good idea to remember that a moment is defined by the force that applies it and the point that you're taking the moment about. This is also like physics. People tend to treat this as synonymous with a torque. So like in physics, you might have talked about torques. Engineering people don't tend to think of them as synonyms because a torque in engineering is usually used to mean a very specific combination of moments. But so in physics 1, when you talk about torques, this is what you're talking about. And say that you have this arbitrary object. So here's some body, and this can be in 2D or 3D. And let's say that here at this point P, a force F is applied. So this is the force vector F. And then let's say that this is the point that you're calculating the moment about. So this is A. Then draw a vector that goes from A to P. And we'll call that vector rho, the Greek letter rho. So let me name these things first. So A is the point the moment is calculated about. A lot of times I'll call that the about point. P is the point where the force is applied. This vector rho is the vector to P from A. And then the moment, which is a vector. So the moment about A is what this means, is equal to that rho vector crossed with the force vector. The intuitive meaning of this so think about like you have a bolt and you're trying to turn it with a wrench. Okay, there are two things that are going to determine how successful you are at loosening this bolt. Oh, three things. One is that you have to turn it the right way, otherwise you're going to. But it's not just about the force that you can apply to this wrench. It's also about how far down the wrench you apply that force. So if you apply 100 newtons of force right here, it wouldn't tend to turn it very much. But if you apply that same 100 newtons of force way down at the end, it would be a lot more likely to get that movement. Okay. So in this case, here's what we're talking about. F. Yep, the force. So if you're trying to turn this, think of the bolt as the about point. Think of this as the point P. You're applying a force F at P, and the rho vector is this. So what it's doing is this cross product is telling you, calculating like a combination of a product of the F and the perpendicular distance from the axis to where the force is applied. It's not good enough to just multiply the distance, the force times the distance from the axis, because like if you're trying to turn that bolt by applying the force this way, that's never going to turn it, you know. That the distance that matters is the distance that's perpendicular to that force. Okay, so that's what the cross product does here. And I recommend a table for keeping track of, so to keep track of the rho vector, the force vector, and the moment vector. So like, for example, so rho, force, moment. And then you can enter in the values like, so say this is 5, -2, 0. The force is 0, 1500, 0. Take the cross product and you get 0, 0, 7500. And you'll do this for, so once you draw a free body diagram, you'll have all these different forces acting. Well, this is rho, force, and moment for one of the forces, then the next force, then the next force. And at the end, when you go to Newton's second law and the moment equation, you'll have this column of things that give you the entire left side of Newton's second law. And you'll have this column of things that give you the entire left side of what I'm going to call rotational Newton's second law, or the moment equation. Okay. It's about any of that yet? Okay, so here's some things about the number of equations that you're going to get out of stuff. So notice, oh, did I skip a couple? No, not yet. Okay, notice. So the first thing is, when you're using the moment equation, that's what I'm going to call rotational Newton's second law, for a single body, you have to use the same about point for every force. And when you're using Newton's laws for a rigid body, if it's a two-dimensional problem, Newton's second law, how many equations does that give? So if it's a two-dimensional problem, you have an x and a y component on all your forces. So two equations. Yep. 2D is like in the plane. So think about how many directions something can rotate in the plane. How many axes can something rotate around in the plane? All it can do is rotate in that plane. And so the rotational Newton's second law only gives you one additional equation. And so the sum of